Assalamualaikum, my name is Sakinah binti Muhammad Saad and I will present my final year project titled Corrosion Inhibition of Mild Stay in 1 molar HCl using Moringa oleifera extract at varying temperature. My supervisor's name is Dr. Nozakia binti Nur Hashim. First, what is Moringa oleifera? Moringa oleifera is a tropical plant that is rich in bioactive compounds such as alkaloids, flavonoids, and phenolics that has shown potential to inhibit corrosion. These compounds contain functional groups such as carbonyl group, imine, carbon-carbon double bond, and hydroxyl that can absorb onto metal surface and form protective layers. Now let me explain the problem statement of this research. First, mycete easily corrodes in acidic environments like 1 molar HCl, causing damage and safety concerns in many industries. This is a major issue, especially in fields like oil and gas, chemical processing, and construction where mycete is widely used. Second, most corrosion inhibitors are synthetic and harmful to the environment. Although they are effective, their toxicity creates long-term environmental and health risks, which is why alternatives are needed. So, this study investigates Moringa oleifera as a green, eco-friendly inhibitor to reduce massive corrosion at different temperatures. Now moving on to the research objectives of this study. First, this study aims to evaluate the corrosion inhibition efficiency of Moringa oleifera extract on mild state in 1 molar HCl using linear polarization resistance or LPR at 25, 55, and 45 degrees Celsius. Second, it aims to examine the absorption behavior of the optimal extract solution at different temperatures using UV spectroscopy. This is to understand how well the extract bonds with the metal surface. Lastly, the objective of this research is to analyze the surface morphology of the corroded microscope using SEM and EDX across the tested temperature range. This is to observe any physical changes and surface protection provided by the inhibitor. Here is the base of the literature review related to my research. Firstly, microscope corrodes rapidly in acidic environments like hydrochloric acid due to electrochemical reduction on the metal surface. Secondly, synthetic inhibitors such as cholinesterase arylphosphate are effective, but it poses serious environmental and health risks. Third, recent studies have shown that Moringa oleifera extract shows promising corrosion inhibition through adsorption of bioactive compounds by forming a protective layer on microscope. And lastly, inhibition efficiency decreases at higher temperature due to desorption, showing the need for temperature-focused studies. Next is the methodology. The method that was used in this study is accurate sample preparation, linear polarization resistance or FPR, and this was used to evaluate how well Moringa oleifera extract inhibit corrosion of microscope in 1 molar HCl using 3 different temperatures. Next, I used UV spectroscopy analysis. This method was used to identify how the extract interacted with the microscope surface. And lastly, surface morphology analysis was done by using SEM and PD. Now I will explain the results and discussion from the linear polarization resistance or LPR analysis. From the result, we can see that corrosion in current density or called as ICOR increased as temperature increased, both in blank and inhibited sample. This is expected because higher temperature usually speed up the electrochemical reactions, making corrosion more aggressive. As you can see, at 25 degrees Celsius, the blank sample had the lowest ICOR, and with Moringa extract, the inhibition efficiency was at 8.29% at 100 ppm and 11.85% at 400 ppm. As the temperature increased to 55 degrees Celsius, the black icon increased, but the extract still showed significant inhibition. At this point, the efficiency was 36.89% at 100 ppm and 33.43% at 400 ppm. At the highest temperature, 45 degrees, which is 42 degrees Celsius, the black sample had the lowest ICOR value, but also the highest inhibition efficiency was recorded, which is 82.96% at 400 ppm. This shows that the inhibitor was more effective at higher temperature. Now I will explain the UV visible spectroscopy analysis. This part of the study was conducted to investigate the interaction between Moringa oleifera extract and microscope in 1 molar HCl FC using UV-vis analysis. In this analysis, three samples were tested. First, the pure 400 ppm extract. Second, the 1 molar HCl stock solution. And lastly, the third sample is 1 molar HCl stock solution that were after immersion with microscope. Okay, as you can see, this spectra, all three spectra show a peak at 211 nanometers, but with different absorbance values. Before the emission, the first sample showed a very low absorbance of only 0.00016. You can refer the orange line. And for the second sample, we issue 1 molar stock solution of HCl. After immersion with mycel, you can refer the blue line. The absorbance became uh, increased significantly to 0.39897. This suggests that active compounds from the extract interacted with the metal surface. And lastly, the third peak, you can for the 400 ppm extract, you can refer the gray line. The absorbance value recorded was at 2.5629, which reflects the high concentration of bioactive compounds such as flavonoids or phenolic acid. Although there was no shift in the wavelength, the increase in absorbance intensity clearly shows that absorption occurred. Now I will explain the results from the SAM and EDS analysis, which help to observe the surface morphology and elemental composition of massive sample. Okay, first let's look at the SAM analysis result. As you can see at 25 degrees Celsius, the Fresnel image of the blend sample shows severe corrosion with rough surface and deep pits. This indicates a high level of surface degradation due to acid attack. And next, at 45 degrees Celsius, 1 molar HCl, you can see that the corrosion became more aggressive. The same image revealed worse surface damage with the more pronounced roughness and corrosion features. This shows that corrosion intensified as the temperature increased. For the 400 ppm at 25 degrees Celsius, you can see it shows a much smoother surface with fewer corrosion peaks. This suggests that the inhibitor began to form a protective layer on the metal. And for the 45 degrees Celsius, the surface condition was significantly improved. The same image displays minimal corrosion and a nearly uniform surface, showing that the extract worked more effective at higher temperature. Next, for the index analysis, as you can see, the blend sample at 25 degrees Celsius showed high oxygen content and some chlorine, indicating the presence of iron oxide and chloride ion from active corrosion. At 45 degrees Celsius, the iron content increased while oxygen dropped, meaning more of the base metal was exposed due to outside layer breakdown. Also, no carbon was detected, confirming the absence of any protective organic layer. For the 400 ppm extract at 25 degrees Celsius, EDX showed higher carbon and even some nitrogen, suggesting the absorption of organic compounds from the moringa extract. The oxygen and chlorine level were lower than the blend, showing reduced corrosion activity. And at 45 degrees Celsius with 400 ppm, EDX showed high iron and carbon content but no chlorine, which strongly supports that a stable protective layer was formed, effectively blocking corrosive ions. To conclude, all of the research objectives in this study were successfully achieved. The LPR analysis results confirm that the Moringa oleifera extract effectively reduced corrosion of mycel in 1 molar HCl with the highest inhibition efficiency of 2.96% at 400 ppm at 45 degrees Celsius. The UV-based analysis showed increase in absorbance after immersion, which indicates the absorption of phytochemicals onto the steel surface. Meanwhile, the SAM EDS analysis further supports this by showing the smoother morphology surface, lower oxygen, and high carbon content on treated sample, which further confirming the formation of a protective organic layer. So overall, Moringa oleifera is proven to be a green, cost-effective corrosion inhibitor and suitable for acidic environments at elevated temperature. Now I will present the recommendations for future work based on this study. Firstly, the extract concentration range should be expanded between 50 ppm and 1000 ppm to identify the optimum dosage that provides the best portion inhibition without compromising the stability of the protective layer. Secondly, the temperature range can also be widened from 10 degrees Celsius to 60 degrees Celsius to stimulate real industrial conditions like pipelines and chemical systems where temperature fluctuates more than in lab conditions. And lastly, the inhibitor should be tested in actual industrial systems and formulated into stable forms such as coatings or gel for easy application and storing.